Yes.
Just let me know. Are you hearing me?
Yes.
Thank you. So I'm from Pakistan. My name is Sohaib Shahid Qureshi, and by qualification, I'm a professional agrologist. I have done MSc honors in agriculture sciences and a business graduate as well from Pakistan. Right now, I am working as a biomass supply chain manager with one of the leading paper and board industry in Pakistan. Since last 11 years, I am managing the supply chain of biomass material for our existing biomass power plant located in one of the province of Pakistan and city in Lahore, Kasur. So I have more than 15-year experience dealing with the similar biofuel management and then fodder crops, particularly for dairy sector as well. So it's a pleasure to meet all of you, and we have a good session, inshallah. So thank you, everyone.
So it looks we can start our introduction freely here. My name is Javier Dooenck. I'm in Yokohama in Japan, and I'm engaged in producing biodiesel, a special diesel from lignocellulosic biomass, which sounds very odd, but it is possible. We have a machine that can do that. We produce a high quality diesel with our system. So you will hear a little bit more later on. Thank you.
Hello everyone. I am Muhammad Umar Khan from Pakistan, Lahore. I have recently did my graduation in mechanical engineering, and my final year project was related to renewable energy. And now I am going to University of South Wales, UK, for my MSc in renewable energy and sustainable technology. So this session would be a great opportunity for me to learn biomass, because my course over there is particularly based on hydrogen fuel, the production of hydrogen fuel from biomass. So this session would be a great introduction to biomass for me, and I am expecting a lot of learning from this session. So thank you very much, all of the speakers and participants.
Good morning, everyone. I'm Chandrasekhar Pal from Czech Republic. I am doing my PhD third year, and I am working with Bio-char, generally sweat/biochar, and we are just applying Bio-char to the soil to release more phosphorus from it. And on the other hand, we are also treating the biochar with some microorganisms for getting more phosphorus and other nutrients from sweat/biochar. Generally, we are doing to apply the biochar or to use the biochar as a fertilizer. You cannot say it's a fertilizer, but it's generally a soil amendments. So we are just understanding how microbes will help us for nutrients released from biochar. So I will explain you everything in my presentation, and it's a very nice platform to share all this knowledge with you. Thank you.
Hi everyone. This is Chandrasekhar Nandigama from India. I am founder of Biofuels. So we are in the sector of transforming the organic biomass and agri waste into biofuel through biomethanation project. The core technology is anaerobic biodigestion technology. So this compressed biogas can be used as a transportation fuel, and it is a replacement for the natural gas. So today I'm one of the speakers. You will learn about what we are trying to do in this sector. Thank you.
Hello, good morning. It's Dr. Shweta Sharma here from India. So currently I am working in one of the leading petrochemical companies of India, and my work is precisely on developing consortia for like particular waste degrading kind of, like whatever the effluent is customized kind of consortia for degradation. I'm basically from the ETP team. So as most of you people are telling that yes, sludge management is being used for this biofuel generation. So yes, we are looking into that aspect also, that huge amount of sludge which becomes a liability for the company. That how can that be used for biofuel generation? Thank you.
It's biomass, yeah. Okay. So I think all of us are pretty educated in biomass. You know what we can do with biomass. We can carbonize it with hydrocarbonization or with vapor carbonization or pyrolysis. We can do gas production. We can do
Steam production,
liquid fuel production, and that I wanted to talk today. We are producing fuel, diesel fuel for the maritime industry from lignocellulosic biomass. So that means you have straw, you put it into our machine, and you get out a very high quality MGO machine and maritime gas oil. And it's really a epoch-making thing that we are doing there. We have a joint venture in India, and we have in total 17 projects around the world. So this will be a real game changer for biofuels.
Actually, I wanted to comment on this. It has to become a game changer because right now the game is always the sun is producing the biomass, which then we are consuming for energy. But with all the talk about electric, people tend to forget that the original energy always comes from the sun, is stored in biomass, and then only has avenues to be converted into electric. Yeah. Without that, you cannot charge any battery. So going away from liquid fuels that can be easily stored, have high energy density, is actually the wrong way out. But one thing where I wanted to compliment Mr. Hans is, once you have those liquid fuels, you have to put it in an engine that doesn't waste 70% of that energy.
Yeah, correct.
And then we are much closer to be able to convert the sun's energy via biomass also into electric or directly into motion.
Yeah, it's important. We have 30,000, 60,000 ships on the ocean, and they are all using fossil fuel at the moment. They are fiddling around a little bit with biofuel, but biofuel doesn't have enough options. You know, it comes from vegetable oil or used cooking oil, and it's very limited. And in the meantime, there are so many competitors for the feedstock that the prices for biofuels went through the roof. You know, a ton of HVO, hydrogenated vegetable oil, costs today $2,600. A ton of heavy fuel oil costs $550. That's just not possible to do, you know. And we can actually compete directly with fossil fuels, and that makes a big difference.
Yeah, and it is a way to convert waste that otherwise occupies space and has other issues into something useful.
Yeah, exactly. You see, the thing is, the UNEP, United Nations Energy Program, they have found out that in the world, 10.5 billion tons of agricultural residue is incinerated on the fields. So that means the energy goes up in smoke, and it creates a lot of pollution as well. PM 2.5, carbon monoxide, carbon dioxide. Actually, it's a huge waste what's happening there. And we are trying now in India with a company called Farm to Energy to collect that material and make fuel out of it.
Yeah, and that is the only way. I mean, people talk also about the plastic waste and plastic pollution.
Mm-hmm.
The point is, plastic is actually made from a natural material because oil originally was plant material.
Mm-hmm.
So plastic as a base is a natural product. Now, pollution doesn't come from the plastic. Pollution comes from people who don't know how to handle it properly. If you are running around and you are willing to accept a plastic bag lying around everywhere, then you are one of the polluters because you are not willing to do something about it.
Yeah.
But if plastic is kept in a proper stream from use to recycling or repurposing, then in the end, it can end up in a pyrolysis process that makes oil out of it again.
Oh yeah, I know. I was discussing the whole morning this matter with a group in the United States that want to fish out all the plastic from the North Pacific garbage patch.
That article, yes.
Which is, I had this idea 2007 when I first read about it. I went actually to Long Beach and met Captain Moore. We had a 3-hour discussion. He showed me his boat and everything, and we came to the conclusion it's not possible to fish it out of the ocean, because he showed me what he caught in a very fine mesh net with a 1 mile run. That was a teaspoonful of material. And imagine how much fuel was consumed. And it's not possible to collect it from the ocean. It has to be captured before it enters the ocean.
Yeah, at the river mouth, at the harbor's mouth. And the other thing is, you don't need to capture it in those fine particle distributions from the ocean, because guess what? Mm-hmm. The bacteria in the ocean already start learning how to eat it up. A recent paper outlined there is 40,000 enzymes available to degrade plastic, and bacteria produce most of them. So if you have an abundant source of food, which is plastic, and which originally is a natural product, because that is what oil is, they learn how to eat it. Mm-hmm. So in the future, if your handphone cracks in your hand, that means you have left it unattended for too long, and the bacteria have grown so much, they eat it all up.
Yeah, it's.
But before that, we should learn how to make use of it and put it back into energy or back into oil.
Yeah,
which is what you are doing.
I like to suggest to capture the estuarine silt of every big river system and refine that material, which contains microplastics, microplastic pollution from sewage systems or non-appropriate sewage treatment systems, and obviously a lot of biomass from the mountains and clay particles and a lot of potential methane that could be utilized.
Yeah.
So therefore, pyrolysis is one part of it, but then gasification, anaerobic digestion as stage one, after it has been, dredged and pumped carefully out of the estuary. But there are many, many opportunities around the world which have not been investigated because it's just too murky. As soon as the fresh water becomes saline and flocculates, you have then a build-up in fjords or build-up in estuaries, like we have here in Tasmania, where there's major issues with tens of thousands of tons of annual estuarine silt. And just like in the Thames in the UK, and the Rhine and Elbe, and you name it, the Nile, wherever there's a delta, you have a flocculation process happening. But nobody, or doesn't seem that anybody sees that material as a resource.
Mm-hmm. Interesting.
For anaerobic digestion technology to biomethane, is anyone wanted to collaborate on technology? We are interested. I'm from India.
Yeah, what I would suggest is that we all put our LinkedIn connection in and connect to each other. We are all very engaged in this field, and I think even if we are not directly engaged, we can support each other.
Exactly. I agree. I have put
Yeah,
my LinkedIn
agreed,
profile.
agreed.
So
We
I'm
over.
interested.
Sorry, Frank?
Yeah, I just want to say that, we have obviously the International Bio-char Initiative, and then the USBI and the EBI, the European Bio-char Initiative. There's a lot of work going on right now by very, not just passionate, but determined companies and individuals. And it doesn't really matter where we are on Earth, as long as we have got internet access, we can very quickly tap into this resource. And that's what we are practicing for years now. And we have been growing this collaboration very actively. So I'm in a very distant place, an island south of Australia, Tasmania, and I work with people every day from around the world. But usually there is a program, and that's what I was wondering what this.
That in the past.
Anyhow, I agree. We can link up. I don't know where Richard is based, but
Richard is in Malaysia, I think, aren't you? Oh, something's happening here.
Yeah, some screen pictures changing.
Rice husk biochar, Andhra Pradesh in India. Oh, something's happening. I don't know what it is.
Yeah, and
our waiting paid off, huh?
Yeah, that's what we are converting into fuel, because most of this rice husk is also incinerated, even in the fields, because they have started now to use it in for biopower plants, but it's a complicated feedstock because it has a lot of silicone in it, and that is a real problem. Not so easy.
Actually, silica from rice husk here in Malaysia is used in a low temperature combustion process to create a amorphous silica that can be used to make aerogels. Because if the silica is burned at high temperatures and it becomes crystalline, you can't dissolve it. But we have developed together with the local university a low temperature burning process where they collect all that material and make it into a aerogel, and the product is already being sold in the market. But this is what you can do with the silica. Of course, low temperature burning also means less efficient energy recovery, but you have a valuable byproduct. Yes.
Actually, I was very much against using rice husk for electric power production, because it's a too complicated feedstock, and the OPEX, the operation expenses, are much too high, because you have to regularly hack off the deposits from the pipes in the boiler. It's terrible. It's a terrible stuff for a boiler.
Yeah, we may need to look into how we do it at lower temperatures, because when you don't have it crystalline, then you don't have to hack it off. You can.
Yeah, that's true. That's true. Interesting. I have put my LinkedIn.
Other type of burning mechanism.
I have put up my LinkedIn address, so if you would like to connect, I'm interested in hearing more about that, because we are working a lot with rice in India.
Let me share the some realities of the rice husk in Pakistan. In Pakistan, basically, rice husk is not the product of the farmer; it's a product of the rice mills. They are basically processing the rice, and then they are using for their own boiler for the energy generation, and the people who are buying the rice husk for their low pressure boiler, they are facing some slagging behavior on the walls of the boiler because of the silica contents we have observed after passing through the boiler is 52% in the bottom ash, and very less fly ash, and even the less nutrients observed in the final ash product if we compare with the wheat straw and wheat compared with the corn stalks burning, and the potash level is around 15% in the fly ash, but it's less than 3% while using the rice husk. And on the other hand, the bottom ash production goes to the 30% higher than the normal biofuels. And the other thing is the rice husk is available in the loose form in Pakistan. It cannot be baled because of the very fine particle, and the raw form, its silica contents goes to it's a natural sand, that the bounded silica, you can say, is around 10 to 12% inherently. So it's so that normally we recommend that the inherent or bounded silica should be below 5% for the smooth boiler operations. So this is another other side of this rice husk, particularly in Pakistan.
Okay, if nobody objects, I start with the sharing. Is that okay?
Yes.
Go for it.
Okay, I go for it. Okay, thank you for giving me the opportunity to introduce our Cambio Fuel, which is made from otherwise incinerated agricultural biomass. It will power the ships of the maritime industry with carbon neutral or even carbon negative fuel. So we have virtually unlimited low-cost feedstock in the billions of tons. Actually, the IEA and the UNEP, they estimate it to be 10.5 billion tons that are incinerated every year, which means about 16 billion tons of CO2 are entering the atmosphere without being, without any purpose. So we hope to change that in the future. Yeah, that's it. It's a simple and energy efficient conversion technology. We need only about 5 to 10% of the electric energy that is required to produce liquid hydrogen, only very small, but we have half the energy of liquid hydrogen with that fuel. It's a drop-in fuel. It doesn't require any changes in the infrastructure, which is very good. We can mix our stuff with heavy fuel oil and go to, how can you call it, B5, B10, B20, up to 100%. Important is also that we can produce locally. We don't need massive refinery-sized plants, but we can produce in small units that can be daisy changed for larger installations. The important point is that we can adapt the plant size to the biomass that is available in the region. A very important point. It supports the local economy. The farmers get money for something, so we are democratizing the fuel industry. I love that. So no Exxon, no Shell. It's all in the hands of the people. Good. We have a problem at the moment with the other biofuels. The question is really, how can used cooking oil become even more expensive than virgin oil feedstock? People don't eat enough French fries is not the solution. It's a very limited commodity and it's a seller's market. Collectors can currently ask any price. The supply of virgin oil cannot be expanded with the increase of demand because we have the plate or tank dilemma, indirect land use changes, EU policies, and so on. So that is really a headwind the current biofuel industry has. There's also a rapidly increasing competition for the feedstock. So the feedstock used cooking oil or virgin vegetable oil, because many normal oil refineries are repurposed to produce HVO, hydrogenated vegetable oil. So for example, in the US, there are several, I think in the meantime, 6 large refineries, and in Europe the same, Shell and so on. There are there is a huge demand increase on the horizon, and that means even higher prices. So virgin oil is criticized for rainforest destruction and for competing with food demand, and Europe has concrete plans to ban palm oil as a fuel. renewable marine fuel, when it's used for marine fuel, it's competing with the aviation. It's another application for the HVO. And the conclusion is very simple: oil and fat-based renewable fuels are not enough scalable. This is what the International Energy Agency said. Drive to greater biofuel usage hampered by high cost and lack of feedstock available. It's really not scalable, this whole thing. So look at that, what's happening. This is, these are the prices on the left side for palm and rapeseed oil prices. That's the feedstock. So the feedstock is already, if you look for rapeseed, at $1,800 per ton. At $1,400 for palm oil. The green line is what we are at the moment selling it for, but we make a nice profit with that. We can even go lower. And the brown line is what the current price for fossil fuel oil is. If you look at the biodiesel prices on the right side, that's $2,600 per ton.
We cannot see it. We cannot see.
You cannot see?
No. Just the writing.
Whoops. That's weird. That's weird. Sorry.
I think you have to F5 or to multimedia to pass on the slides to the next, because
Yes. Or maybe you can do it to full screen, so then it will be changed. I think
it's full scale. It's full scale. So I'm not sure what that is. Why that's not showing. Very weird. You cannot see at all.
No, we only see carbon negative diesel from lignocellulosic biomass. Just the
only one slide. First
only
slide.
one slide. Yeah, second slide.
That's not changing.
No.
Yeah, but that's not something here in my computer. It's something that is in the system. Okay. Yeah, that's unfortunate, because
you can share again.
That makes presenting
Yeah.
completely worthless. Oh,
You can share again.
Will you please click on the third slide? Just click it on the third slide.
On which one?
The third slide, or use your up and down arrow keys. Yes.
Yeah, now
It's working now. It's working now.
Yeah. Okay. Then we run it from here. Okay. I don't go through the whole thing again. If the full screen doesn't work, then let's go through the small screen. But here you can see, I hope.
Yeah, we can see now.
Yeah, you see what's happened with the vegetable oil prices. They are really going up through the roof, and that is through this competition from repurposed refineries, fossil fuel refineries. It will further increase and push prices even higher. It's unbelievable what's happening there. Okay, so our solution is pretty simple. We take lignocellulosic biomass, which is completely without limits. We use biomass waste like sugarcane trash, orchard pruning residue, for example, from in California, from almond shells and walnut shells and things like that, and also the pruning residue, which is a very, very good feedstock. When they have harvested, they cut the trees, the branches of the trees. So then our main target is the otherwise incinerated fuel residue, rice and wheat straw. And that's quite amazing what's happening there with the incineration. So 16.6 billion tons of CO2, 9.8 billion tons of CO2 equivalents, 1.1 billion tons of smog precursors, and 66 million tons of PM2.5 go in the air through this. And it's estimated that about 1 million people in the world die prematurely due to this kind of emissions. For us, it means it's an unlimited potential for the production of carbon negative biofuel. Why carbon negative? We take more. We have a side product that is bitumen, and much of the biomass is or the CO2 is sequestered in the bitumen. So in the end, our fuel emits less CO2 into the air as if you are burning it in the fields. So this is what we are doing. This is a project in the US. It's in the Glades in Florida. They before harvest, they incinerate the sugarcane trash. There are, in the meantime, other harvesting methods there. And yeah, it's good for 800,000 tons of fuel oil that we could produce there. This is our project in India. They are harvesting the farm to energy is a company. They harvest the rice paddy and roll it up and bale it. And they deliver it at the moment to thermal power plants for incineration. But the yearly potential is just scratched on the surface. It's 20 to 25 million tons, which is good for 5 to 6.5 million tons of fuel oil. To give you a comparison, Maersk, one of the largest, the largest shipping company in the world, uses about 10 million tons with their 750 ships. So we can make quite a big dent already with the feedstock that's available in Punjab. So we have in total 17 projects in the pipeline in the US, in the Philippines, in Vietnam, in India, Sri Lanka, Mauritius, and Morocco. Why is that? Will that be successful? Because we have an increasing transparency in the shipping industry through IT. The ships are much closer observed than it was before, so it can be very easily calculated how much CO2 they blow into the air. And the industry, they have their own agenda. They all, like Amazon, like Walmart, like IKEA, and so on, they all want to lower their footprint. And so they are, in the end, they are turning to shipping companies that are offering low carbon transportation. Okay, next. How do we do it? We are using a zeolite, a catalyst. It's also called a molecular sieve. It has in principle small openings that crack the material. I cannot go into much detail, but that's what we are doing, and it's working, which is nice. So what we are doing is we are taking the long hydrocarbon chains of the lignocellulosic material and crack it into shorter chains, and they fall into the range of the diesel. This is a 500-liter test and demonstration plant per hour. So that is about 4,000 tons per annum production. So this would be a standard for a village or for a small town to produce their own fuel for their trucks and agricultural machinery. They don't need Shell and Exxon anymore. Okay, we haven't, I don't want to go into many details. The interesting part is when it's used in the ship, there is Daphne Technologies, a new company in Switzerland. They have a new exhaust gas cleaning system, which will make our fuel better than zero. We can go carbon negative. And we don't have harmful substances because this filter is filtering out 95% of sulfur oxide and nitrogen oxide, and they make fertilizer out of it. Very fascinating technology. I really love it. So this is something you should keep in mind, because this can also be used for diesel power plants, even for conventional diesel power plants, not only with our fuel, but conventional diesel power plants can use this as well. It's a good company.
This will convert these things to electricity?
Sorry?
This machine will convert to, produce electricity?
Yeah, you know, you
in
have
the
diesel
ship,
power
as
plants.
you mentioned.
You have diesel power plants all over the world, yeah? And this filter is actually filtering out all the harmful substances from the exhaust of diesel power plants.
Okay.
So the Philippines have, for example, 1.6 gigawatt of diesel power plants, a huge number of diesel power plants. So the question is,
what is the feedstock price in your country right now for the per ton, on average of all feedstock you are using?
Yeah, we just have to collect it because it's a problem for the farmers. They are the Indian government had even high fines on it to incinerate it, but they don't have the money to collect it. So we do them a big favor in just collecting it. And of course, in the long run, we will have to pay for it, but it will be probably in the range of initially $10 to $15 per ton or so, but it's more than nothing. And at the moment, for them, it's a headache.
Yeah. And
Yeah,
do you work with sweet sludge as a
Sorry?
feedstock?
Sorry?
Sweet sludge as a feedstock?
Wet sludge, no. We need to dry the feedstock, and also we have to get it down to about 5 millimeter size.
Okay.
Yeah. We are using a special machine from the US that is producing down to 200 micron powder from it, and very energy efficient. It's not a shredder. It's how can you say? It's a kinetic disintegrator, which is drying and disintegrating in one stage, and it's a very smart system.
Okay.
Yeah, no sludge is unfortunately not possible, though I can tell you there are quite a lot of attempts to dry the sludge and use it, and then when it's dried, we can use it actually. Yeah, but the energy to dry it is quite high.
Yes, I agree with you.
But we can process sewer sludge. That's not a problem. It's possible. Yeah, and yeah, again, we have a very sound financial model for that. We have an ROI with our plants in 3 years, which is pretty good, and a levered internal return on revenues between 19 and 35%, which is quite attractive to investors. So this is all moving at the moment, and thank you very much. So become part of it. Thanks.
Yeah, thanks as well.
Oops, slides are not changing. Yeah, that's weird. I don't know why.
It was possible to see your slides thereafter, so it was good.
Yeah. Anyway, it's good. Yeah, there are some comments. Round bales of rice straw are costly because of low payable load on trailer. What about square bales? They do both. They do both, but the round bales are easier to produce, and the square bales is also possible. They have both balers, square and also round. At the moment, you know, they do about 120,000 tons per annum at the moment, and in 2 months, and that is just the tip of the iceberg. And so they are learning, and we are learning, and if it's really a problem, then we have to change it. The thing is, we place the conversion plants where the feedstock is. We are not putting the conversion plants in one place and let the feedstock be transported to that place. That's not necessary. We need, for one unit, we need 15,000 tons per annum feedstock. That's not much. You can have that really in the vicinity, in the close vicinity.
I think it is a very important point that Hans mentioned, that the units get close to the raw material, because transportation cost is killing many businesses
Yes.
that are related to waste.
Yes.
Spot on. This is why it needs to be decentralized technology. And it doesn't really matter if it's for solid carbon use as pure organic carbon, like Bio-char and feed char and filtration char, construction char, and so forth. So the closer we can do these things near the source, the better, provided we can make use of the thermal energy. At the moment, with our mobile units, we virtually forgo the thermal energy. We just virtually, as long as we don't pollute the air with particulate matter, we can go into a vineyard or into an orchard and carbonize the annual prunings. But of course, as soon as you go industrial scale, like Hans described, it would be ideal to have facilities that can optimize the opportunities close to the feed sources. And so it needs to be scaled accordingly.
Yeah, another point that we all have to remember is we have harvesting seasons, and some are extremely short. In India, for example, the harvesting season in Haryana and Punjab are just 2 months. So in the 2 months, you have to do your job. And then you have to consider what to do the other 10 months. You have to bridge that, yeah. Of course, there is also other waste material, but we have also a strategy to use a purpose-grown biomass. In India, in Thailand, and the Philippines, there are beautiful grasses. They are called Napier hybrids. They are C4 grasses that grow extremely fast. We have experienced yields of 600 tons wet per annum per hectare. 600 tons wet per annum per hectare. So dried and shredded, we could produce about 45 to 50 tons of fuel per hectare, which is unheard of. If you look at Jatropha, they are talking about 1 to 3 tons per hectare. Yeah, even palm oil, which is the most productive one, that is just around 8 tons per hectare. So we can make a big change also with the feedstock. Low-cost feedstock, plenty available, and high yield.
Yeah, very important.
Yeah.
The key to waste utilization always is the avoidance of transport.
Mm-hmm.
That is why most of the waste ends up in the wrong place, meaning being burnt and polluting the air, or lying around in landfills.
Yes, 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 that's a big problem. You see, you have to keep in mind that 40 to 50 kilometers is really the threshold, and that's not only the commercial consideration. That is the energy consideration. You are using more energy to transport that stuff that is finally in the product, and that cannot be. You know, we have to really think about what we do with the energy. So that means always close to the source, and in scales that can be supported by the feedstock in the vicinity.
Yeah, fully agreed.
Totally agree.
So, who is SS, please? Yeah, open your presentation. So hype, Shahid. So hype.
Yeah, Hans, thank you. So Javier, did you allow me for presentation?
Yeah, Javier.
So so it's visible to all participants.
Yes, it's visible.
Yes.
Thank you. Thank you, Hans. It's a very good information you have shared with us, and let me share another other picture, which is basically you are talking about the prices and the feedstock availability. So the Pakistan has a very high volatility right now, because the lot of the boilers and companies, industries who are more focused on the green energy, because coal prices are shoots up, and HFO and gas prices are also not in control. And being a developing country, Pakistan is facing the challenges and competing with the import products, because our products are costly right now, and the import is cheaper just because of the high energy cost is one of the critical factors. So let me talk about today about how to mitigate this risk, especially when sourcing the biomass and this logistics in the highly volatile market of Pakistan. So do let me know if you feel that the slides are not changing. So I'm on the second slide, so it's visible for all participants or
Yes,
not?
yes, it's visible. It's
Can you put in the
yes.
full slide mode?
It's a second slide.
Yeah, it is a second slide, but can you on the bottom screen on the right put the full slideshow? Full screen.
I just read it.
That one, yes. Yeah, okay.
It's
Thank
okay.
you. Yes.
Okay,
yeah,
thank
it's
you.
okay.
So just let me explain about the agriculture landscape of the Pakistan. Where you can see it's Pakistan total area of is around 79 million hectare, and out of 79 million hectares, 36 million hectare is a cultivated area in Pakistan. It's a cultivable waste and other urban and 5.9% is the forest area in Pakistan. So it's if to talk about the cropping pattern in the 5 different provinces of Pakistan. So we have existed 22 different cropping pattern that are exist in Pakistan under different climatic condition. Like the people who cultivate the wheat, they cultivate the rice or the cotton, and similarly those who cultivate the sugar cane, and they cultivate with some intercropping of some fodder as well. Similarly on the corn and the potato is one of the cropping pattern. So these are the different cropping pattern that exist. This cropping pattern shows that we have a 20 plus different biofuels available in Pakistan. But there is an other side, that is an intensive cropping, and cropping intensity is 159% in Pakistan versus 142% in India. That shows that we are quite intensive in terms of farming, and the only reason is the low income of the farmer, and farmer to get the revenue from the field, so they cultivate 3 or 4 crops in a year for the better profitability. But the other side is that this intensive cropping is very harmful for the soil organic matter balance, because we are depleting the soil nutrient profile as well. With this intensive cropping, we have to give some fallow period as well. But the only reason is this, that the average farmer size, or the farm size of Pakistan, is less than 10 acres, which is too small, where mechanization cannot be adopted fully. So we are not even not in the semi-mechanized country. We can say we are more towards the manual harvesting practices in this era. We have in small patches in some of the provinces. We have big land holdings, but still the practices are not aligned with the collection mechanism. So I will take next couple of slides. So this is the one quick review or overview that give you an idea what actually in the Pakistan the agriculture situation is there. So talking about the biomass sources in Pakistan, in the world there are different sources exist, from the agriculture and the crop residues, and the forest residues, and the municipal waste, animal waste. But as I told, that Pakistan has a forest area is around 5.6%. So we cannot take dependency for the forest residue for energy generation. Similarly, municipal waste is very unorganized, and there is no organized structure in Pakistan because of no segregation of the municipal waste at field or the source level. Animal waste is yes, it's used in the bedding in most of the on the farms and in the poultry and in livestock, but it's not used as because of the refining issue, and we cannot use in the biogas right now. So the 99% industry in the Pakistan sourcing green energy only from the crops or the agriculture crops residues. Even not the shrubs or the grasses the Hans are talking about, in that India has a abundant availability of, yes, in the Pakistan there is also abundant availability of grasses, but there are some other issues, similarly the chlorides content and some the high moisture and the ash contents in those grasses is the major challenge right now in Pakistan. So as I told that there is a high share of this manual harvesting versus the mechanized harvesting, because this tell us what actually we are wasting in the field. Well, Pakistan is producing above 40 million tons of biomass, but the net availability for the power generation is only 15 million tons, because a lot of waste is wasting in is the right term is to, we are wasting the waste in the fields. So because the low collection efficiency and the less availability of the labor, the main product, the core product is not the biomass. The core product is the grain of for the farmer and the industry. So this is again a byproduct, and farmer is dealing this byproduct as a waste. But if talk about and you can see the manual and the mechanical harvesting trend. So there are different for the in term of different acreage, greater than 12.5 and the lesser than 25 acres. So you can see the 70% is the manual harvesting and only 30% is mechanical harvesting. And mechanical harvesting is only on the that is mean that we are using the combined harvesters for the rice and for the wheat mostly, but there are no combined harvesters for the cotton, for the corn. Pakistan has the four major crops: is wheat, rice, corn, and sugar cane. So there is only limited the mechanization, the wheat and the rice, but the corn, cotton, the sugar cane, they're still on the manual harvesting and the manual picking on the in there. So it's 15 million ton that is available, but again there are certain losses by collecting. We go deep down in the field, and when you start the collecting, what actually happened. So this is the major biomass availability calendar in Pakistan. If you see, there are 16 different biofuels in different seasons available, but the available window is you can see is just of 3 to 4 months. So 80% is basically available in this. You can see. It's now clear to is this slide is visible to all participants?
Yes, it is very clear.
Okay, so you can see it's just 80% is available in April to July, and rest of the fuel is very limited. And about this 80% is only 50% we can collect, or the industry can collect, because farmer has a lot of pressure. So just 25 to 30 days of harvesting span, and the farmer is more focused to handle its grain. He's not much focused to handle his byproduct, with the price difference is too big between the byproduct and this core products. And similarly, there is another concept that farmer is not getting the price of their byproduct as a byproduct. They are getting the price of their byproduct as a waste. So so this is another challenge. And then is as I told, that the manual harvesting is share is high. So there is a challenge on the labor availability, because labor is engaged on the core product, and they are not much focused on this collection of this biofuels. So if you talk about the scenarios of biomass market in Pakistan, so you can see that there are two different realities. What's happening with the manual harvested crop and what's happening in the mechanically harvested crop. So 85% of this manual harvested biomass is going for the animal fodder, especially the wheat straw and the rice straw. and the rest is a 3% is for the domestic burning, and then 5% is for the brick kilns you are using in for their burning, and industry are using only 5% of this manual harvesting. Rest is a 2% of the burning in the field. While if talking about the mechanically harvested, you can see that 80% is left in the field for the burning. So that is a major reason for the smoke right now in Pakistan. And then the second is this, that there is a 8% share the domestic burning, and only 5% is a collection efficiency for the animal fodder. So the both situation are the vice versa. And similarly, there is a brick kilns who are using the 3-4% of this mechanically harvested. But the only issue that we have a not right equipment for the collection of this mechanically harvested waste stock. Yes, we have a field balers, we have a local made shredders available, but the practices are not aligned. If we talk about the echo or the class balers to use in the field balers, we have a sowing of this corn on the ridges rather on the flatbed. And similarly, there are no line spacing, or the row to row distance has been maintained in the wheat and the rice. Majorly on the broadcasting we are using. Some are farmers are using on the high bed raising, or some are using on the zero tillage. So the practices are not aligned. So you cannot dependent on the field baler, because if you use a field baler, there is a high wear and tear and the high damages of this machine. So the collection efficiency is low in this situation in Pakistan. So what to do while sourcing this biomass in Pakistan condition? The best model is to transform this agriculture into energy, that we have to take the 50%. Industries have to take the whole of 50% of their collection in hand, and they have to establish their own collection sites and processing sites for where they should store it, and then move to the industry and schedule the arrivals accordingly. The 30% should be the small contractors that should be outsourced, and where this is a long-term contract with this potential fund, because there is a cash flow issue with the contractor. So the industry needs to establish a link with the contractor, where they need to bound them for long term, because otherwise I told it's a very volatile market, and if a supplier get a very good attractive price from another industry, he will not bound, and he will supply the material in season to another industry. So this is another big gap in our market, where there is no formal contract has been placed between the industries and the contractors. So there is only a verbal commitments that are agreed between the industries. So this should be established, and in this condition, but I understand in my experience in the 11 year dealing with this biomass supply chain. So I observed that we cannot give much share to the farmer, because farmer has to focus his own core product. Whatever the practices we have to develop, we have to collect from his facility, and we have to give the ease of this farmer to realize him that yes, his core product has to be handled for the food security point of view, and similarly for other core industries who are working on it. But this byproduct should not be wasted, and only the 20% share logical that seems to be industry can give to the farmer directly, who can supply their products to their to industry door, because farmer need has a limited logistical arrangement at their facility to handle this biomass. But to maintain the price and for the other tax legislation, it makes sense to give the 20% share of the farmer during the season, and those should be around the industries who are located to give maximum share to those farmers. So this is a proposed model to mitigate the risk in this high level. You can see on the right side there is a existing wheat straw supply chain in Pakistan, where you can see the 90% is the contractors, the small contractors who are going to the field, do the agreement with the farmer, and they supply to the large contractors, and they finally give it to the industry. and only 10% are the farmers who are giving wheat straw to industries. But this proposed model is that 50%, as I told, that 50% should be owned by the industry, where they have to do a joint venture with the harvested residues, and then they involve their logistics contractor to collect residues from this field to give an in-transit space or the storage area where they should process, stack it, storage and baling and the mobile baling and shredding. The trailer mounted equipments are available for the baling and shredding of these biofuels, and then stack it their facility and then scheduled to their industry. And the 50% should be contractorized, so the 30% should be the contractors and the middleman that can outsource contract to maintain the price, and so that they should know that what are the industries offering, and more or less on the 5% profit they can work on those values. And similarly, the 20% of the farmer, so it's a cumulative 50% of the contract and the farmer share. They can either directly go to the industry, or they can supply to your collection site located in the remote area, as Hans told, that at 40-50 kilometer is logical for any collection sites for this model. Talking about this biomass logistics, so you can see there are different loading and the transportation mechanism in Pakistan. Here there are different pictures. There's the corn stalks, the cotton sticks, and the rice straw, and the thresh wheat straw. You can see all are loading with the tractor mounted trolleys. The corn is the low density. The long corn stalks has a low density. You cannot carry more than 4 tons on a consignment. So it means that this is only viable from the 10 to 15 kilometer radius where you can collect and process it. You cannot ship it in loose form to the above 100 or 50 kilometers. Similarly, cotton sticks has other constraint. It's a similar weight, but the high seems to be a high bulk, but the weight is very low. So it's from all sides. From field, it's loaded in a manual, and there is an unloading also manual. So loading and the unloading, it's one consignment if it contains a 10-ton load. So it's a 4 hours laborious job, which is a big challenge that industries are facing. And if this trolley cannot complete a 1 trip, 2 trip a day, it cannot compete with the offered price of the industry of the core product, because you are working in the same area where there are 30 consignments available, and those are engaged in the season on the grain, and they are not engaged on this handling of the biofuels, because the price, the people who are the labor who are working with the grain, they are getting the high price because on the one trip, but with the when the price is low, second is cannot achieve the required salaries by labor if they do a 1 trip a day with this handling with these trolleys. So contractor is responsible for these all activities from a field to the center, and if there are any blockages on the industries and boiler goes shut down, there is a huge panic and a very upsets occur in the field, and a contractor may leave the business or shift their business from. So to convince the biomass transporters, there is a proposed mechanism. Instead of going for the manual trolleys, as I showed in the previous slide, we should, and that's time consuming. There is other mechanism that has developed by me with the passage of time, is that we need to trailer mount it with 40-45 feet trailer with a prime mover, so we can load a maximum in this material. Maximum material can be loaded and follow the road safety legislation, because the trolleys, manual trolleys, are the unsafe to handle, and it's time consuming, and there is a 30% time saving with these trailers type loading. And similarly, there is a manual small bales handling and the loading, which is 25 to 30 kg bales, which has a high labor cost and a low bales density, that needs to be shifted in the mechanized loading. and with handling with the MHEs, with the material handling equipment. So these bales should be the medium to the high density. As I told, that field baling is not much successful in our country, and we need to establish the strategies to collect this biomass from the field, and then we have to process it at our collection site, where we need to put the high mechanized balers or the shredders, and then bale it, and then use these material handling equipment to load the material. To that is the time saving and this cost saving. So this is this need to be follow. And finally, when you talk about this, so the best option, because we cannot get rid of the loose handling of the biomass. So the best strategy is the sourcing of the 80% in the season for the stock purpose, and the give 20% of the market share for the non-stock. You can buy, the industry should buy 20% whole year. So that will help to split the working capital. It's a price stability and to make a rational fuel mix. And obviously there is a freight optimization. If you go for the 70% in the baled material to supply to the mill, and 30% the loose material, because loose and bale ratio should be maintained. We cannot get rid of the loose material. It's a high share. So there is a development that has to be followed, and this need to for the best KPIs. So the ultimate goal is the cost effective and the less competitive and the high calorific value of biofuel supply for the industry to compete with the coal and the HFO, because I saw the coal prices right now in Pakistan are above $180 per ton, and the biofuel prices are the $50 per ton. And the heating value, no doubt, is a coal is a double of the biomass, but biomass prices logically is a very significant difference. So to maintain these prices, or to cut down these prices, we have to go to this strategy. So finally, for the efficient biomass supply chain, we have to avoid the competition on a one fuel. As I told, 17 different biofuel exist. So we have to avoid the competition. We need to give a equal share or maximum share to those who are abundantly available. Then there should be the low prices for the high calorific value to get the maximum MMBTU per ton advantage. The working capital can only be split with seasonal buying, and then we should avoid the yearly holding costs, because fixed costs are also involved, and then there's investment costs while holding the material for whole year. And to secure the volume, there is the only solution, the fuel flexibility. And we should avoid the stock out position, because normally in the winter there is a stock out position. So the focus should be that we have to establish those fuel which are available in the winter season. That should be much, and there's a moisture constraint as well. So we need to make a mix, that how to give the share as a 30% the winter and the 70% of the summer biofuel. So this could be the ultimately for this efficient biomass supply chains crux, or you can say, in dealing in the Pakistan in such a high volatile and informal sector. We need to establish these strategies or practices. So this is all about from my side. Thank you, Javier. And this is my details, email address. You can touch me, approach me, and take a further discussion. I'm available on the LinkedIn, and we can discuss more about it, and you can take any information from me. Thank you very much.
Yes, thank you, Sohaib. And I'm requesting
Okay, the screen is being shared, but not at full size. How come? 1 second. Okay, is everyone able to see the screen in full?
yes.
Okay. What I'm going to do today is announcing a new type of engine. This is in direct consequence of what Mr. Hans Dooenck explained, providing opportunities for biofuel to be made from any type of waste materials. These materials need to be converted into energy. Now, the only way to do that, actually there are only two ways. One is by burning and making steam out of it. The other one is by burning it in a engine. And as you all know, the reason that we are all talking about electric engines is because electric engines are efficient by themselves, but the electric energy still need to be provided. And the reason that we are talking so much about electric is because the current version of an internal combustion engine is somewhat between 25 and in the form of diesel between 40% maximum efficiency, which means we are wasting more than half. And what I want to introduce today is, without giving away how we do it, because this has patenting issues, is a new type of engine which has twice the power compared to a conventional engine, half the weight, and it can take all types of fuels. So we hope with this presentation to start a new era for internal combustion engines, because when people stop talking about electric, they'll realize the actual energy comes from the sun and becomes biomass, which then has to be converted. And in order to start this new era, obviously we need to have some intrinsic benefits that were not available until now. We believe this to be the most efficient internal combustion engine ever built, but it may never be built if everybody keeps talking about electric and thinks electric energy comes from lightning or somewhere else from the sky. Everything electric? Yes, but only when it is converted from a source of raw material that contains chemical energy. Now, where did that chemical energy come from? By growing plants. So even the fossil fuel that we are currently all using is nothing else than a plant source that has been converted and depolymerized to become oil. How can this chemical energy be converted? You have to burn it. There is no other way. It has to be oxidized. When you oxidize it, you have the reaction energy to be converted either into steam, and from there via turbine into electric, or you directly use the gas pressure of that combustion to convert it into electric energy. The problems we all know. Yes, we have some emissions. You can never get away from those emissions. But if the emissions create only 25 to 40% of the energy that is available, then we have a lot of unnecessary waste. We have previously talked about a threefold catalytic biomass approach, which is something that Hans-Henning Dooenck also mentioned. He mentioned biomass to energy via catalytic approach and zeolites. We are also we have some extra noise here. Okay, just like the biomass can be converted to energy via a catalytic approach with zeolites, I already mentioned previously that we can convert silicates to catalysts made out of zeolite, and those can also convert plastic to oil. So the way how all this works is shredding and separation. Biomass in an anaerobic digester becomes biogas, which can be used in an engine. Plastic via catalytic conversion can become oil. And this plastic doesn't even have to be clean. The biomass contained in it also can become oil, which removes the preparation costs. Now, the biogas as well as the oil then can be converted into energy via our new engine. And we are aiming at an efficiency between 50 to 60%. Anyway, just for your info, this is the previous work which we have done on biomass shredding and anaerobic digester. These are the cleanup modules and the biogas storage. And this is our pilot plant design for converting plastic mixed with some biomass to oil. Now, how does this engine convert more energy out of the existing chemical energy than all the previous engines that are currently known? We are talking Otto, Wankel, 2-stroke, 4-stroke. The reason is actually quite simple, and it is in the name. We call this engine Hyper-X PDT, whereby hyper stands for extra large expansion, meaning when you have a normal engine, you compress 1 to 10, and when you explode, you decompress 1 to 10. We can compress 1 to 10, but we decompress 1 to 40, which means we are using all the pressure in the cylinder to convert into motion. This is how more energy can be extracted from the same amount of fuel. Now, what else does that mean? It means there is no more noise coming out of this engine because the pressure is converted into energy, which means there is hardly any pressure left. So we don't need silencers for this engine. We have less parts, less space, less weight. The other way how a normal internal combustion engine loses energy is by heating up. And in order not to fail the engine, you have to cool it. Sure, in our case, we also have to cool the engine. However, we do this with a directed injection of water to create steam. The steam then provides pressure that can be converted into motion, can be converted into energy, which means the energy previously lost in the cooling process is not lost anymore. And last, a normal engine has friction, which loses energy, and it creates wear. Our engine is called a PDT because it has almost as little friction as a normal turbine. However, when you have a normal turbine and you hold the shaft, the medium will still escape. In our case, we have a positive displacement turbine, which means it behaves like a turbine, but when you actually hold the shaft, no more medium is escaping, which means bypass losses are avoided. At the same time, Our engine is not a 4-stroke, not a 2-stroke, but a single stroke. Because of that, we have one explosion every turn of the shaft. And that means for the same speed, we have double the power. But because of the design, the weight and the size is half. Now the 20 to 30% more efficiency is coming from the fact that we harvest all the pressure as well as the heat generated. And then, in order to make this engine truly versatile, it is constructed as a modular unit. That means you don't buy a 3-cylinder, 4-cylinder, 5-cylinder, V8 or V6. The engine is composed of a single module which can be stacked. So the number of cylinders is just determined by the amount of torque required for the application. So they simply can be stacked to create more power. Now, when it comes to industry, size and weight of any industrial output is always determining the baseline for production cost. And in our case, we have half the size and half the weight, which increases the efficiency of the whole system of producing this engine, and it reduces the cost for the consumer. At the same time, any application where this engine is used will leave more space to be used. In the case of a car, for example, we have more space available for the passengers, or we have less space needed for parking. Now, with piston that removes has removed friction, we actually do not need to rework the engine or melt it down and recycle it that way. The lifetime is expected to be almost double compared to a normal engine. And the reworking is a simple process that will put the engine back into a almost new state and can be done indefinitely, which means this is the engine which you can buy for your car and then your grandson can inherit it. This obviously saves a lot of energy in the industrial process of making this engine, and therefore all the CO2 emissions that come with it. In mass production, we expect this engine to be less costly, because if you have less parts and less raw material involved, you can lower your cost. Apart from that, this engine doesn't require a lot of parts that are auxiliary parts for a normal engine. So radiators and the whole cooling system that is present in an ordinary engine, whether it's for a car, truck, or a generator, is not required. Instead, we have a minimal setup to inject water only in strategic important places. And from there, we harvest the energy that is created by the steam expansion. Silencers and catalysts for the exhaust are also not required, because a longer burning time in each cycle allows full combustion without the need of having the exhaust gases treated by a catalyst. And finally, we may have also avoided oil contamination by using gearbox oils, because the engine itself with the low friction characteristics can be constructed with ceramic, and because of that, oil or lubrication in a conventional sense may not be required at all. Oh, there is one more thing which we have left out in this presentation, and it has to do with gearboxes. Okay, this engine can obviously be used to use any biogas or even hydrogen, ammonia as fuel, but also any of the ordinary fuels, including heavy-duty fuel oil. So applications as generators and marine engines are easy to do with this engine. Now, hybrid drives is an interesting proposition, because if you buy a Tesla, you have an electric motor there, but you don't have a hybrid, which means if no charging is available, is a problem. This engine is actually designed to run without a gearbox. The reason for that is we can have speeds that are way higher than a conventional engine, but we can limit the amount of fuel that is being consumed at those high speeds. Because of that, we don't need a gearbox. Now, you might be aware that the gearbox is a very costly part. So avoiding that makes all sorts of applications way cheaper than they are currently, because this particular part is not required. And it allows you, or it allows Elon Musk to put an engine of our make as a piggyback to his electric motor and immediately have a hybrid coming out of it, because the drivetrain that is existing can be used as it is. Other applications, obviously aircraft, because lighter weight provides more efficient transportation. Handheld tools, who wants to hold a heavy tool if you can have one half the weight and needing half the fuel to carry around? Turbine replacements, because we already have some form of turbine, but with a higher efficiency. Pumping, air engines, small big bikes is another one, whereby I'm a big fan of the bikes. With this engine, you can put the engine actually in the hub, and you put one in the front and one in the back, so you have an all-wheel drive, at least for a motorbike. So obviously, Ron Dennis will be right by saying that the future engines will be much greener. However, while I have shared with you all the benefits of this engine, I haven't shared with you how we are doing it. And that has reasons which are suited in the legal realm because of patenting. We have all the designs ready to build this engine. But in order for the market to accept this, we still need to do a prototype performance verification with IP, and also we have to prove that the lifetime estimate that I have given can be verified. So in that regard, we are looking for collaborators on the technical as well as the financial side. And I can be contacted at my Gmail address. And I leave you with this: for a better environment around us, we first need to have better thinking within us. Thank you very much.